the last subject of this lecture. It's all about this very nice nonlinear control technique. Very nice in the sense it's very popular among the nonlinear control techniques, called feedback linearization. Need I remind you, if you have your, sorry, I just need the blue color. If you have your nonlinear system, okay, let's call it S, nonlinear, okay? So how should I say it? I'll make it like this, nonlinear S, okay? What you want to do is you want to build a feedback. You want to build a feedback, okay? Gamma of X, so this has the state X, and you want to feed this to the input of the system. You want to feed it back to the input of the system, okay? Right? Let's just see alpha X plus beta XV, okay? So also you have here a beta depending on the state X, okay? Also taking the state, and then you feed it here, and you would like, and here is another input V, okay, and this is U, and the idea is that you would like this guy, this whole new system, okay, let's call it sigma, okay, you want to have this guy linear. That's the idea of feedback linearization. So you would like to use feedback to cancel in some sense the nonlinearities. Of course, later on, since you have, you continue, you can build additional control, of course, and you can stabilize the system and so on and so forth, okay? So this is what we do. And we have several types of linearization. Input-output linearization, as well as input-to-state linearization, okay? Need I remind you, and I'm telling this to Florian, these, even if these are in Romanian, I'll also show other slides in English. So I'm just going to translate as I present the slides. So this is called input-output linearization. That's what the title says, okay? Okay, so it says here that linearizing the state equation doesn't necessarily linearize the output equation, okay? And look at this example, okay? This example. This is a system with two states, and with this very simple linear output. Even if you do feedback linearization and you take the input of this form, because the idea is that you would like to cancel this nonlinear term, okay? You'd like to cancel this nonlinear term, okay? And in order to do that, you pick this input, and the new coordinates, okay? And you get this, thing, okay? Z1 dot is Z2, because Z1 dot is X1 dot, and is this one is Z2, because Z2 is A sinus X2. Okay, so indeed it is Z2, and Z2 dot, if you look here, Z2 dot, so Z2 dot is, from this equation, is minus A cosine X2, plus U, times, because I'm doing the dot, so minus A, okay, times X2 dot, okay, and X2 dot, okay, X2 dot is, look at this equation, is minus X1 squared plus U, okay? And if you pick U to be X1 squared plus 1 over A cosine X2 V, and substitute it in this equation, you end up with z dot equal. So it's linear. This object is linear, but look at the output. Output is x2. x2 is arc sinus z2 over, and this is nonlinear. So there isn't much gain you get from this. So you'd like to do input-output linearization. You'd like to do input-output linearization, okay? And you pick this input, okay? So input-output linearization, okay? And then you get this guy, okay? The price of this thing is to keep some part of the dynamics nonlinear. So you cannot completely linearize, totally linearize this. You leave some part nonlinear, but it's much better than the original system. And in this case, because you can't leave this part of dynamics that's left nonlinear, it's about raises the question of hidden dynamics. Hidden dynamics. Okay. So what it says here, if you perform this linearization, this part of the system that you do not see here any longer, you don't see this any longer. This is unobservable dynamics. Unobservable dynamics. This is unobservable dynamics, okay? Okay, so a control with stabilizing the output for some constant value, for some constant non-zero value, leads you to have, for instance, for this system, this type of equation, okay? And you have a problem of internal stability left. Is this stable or not? So things are changing a little bit. Now we have some notations and definitions to extend all this discussion to the general case of nth dimensional systems, okay? First of all, we talk about vector fields. And now it's a little bit of differential geometry we have to introduce. Differential geometry is hard, but, well, it's difficult to understand and to read differential geometry, but that's life. So you consider a mapping F from a set U to Rn to be a considered smooth. That means of class C infinity. Okay, that means infinitely differentiable and all the derivatives continuous. That's what the meaning of smooth. Okay, where U is an open subset of R. U is an open subset of R. Essentially, the application F associates to each point in U a vector in Rn, because it's defined on U with values in Rn, and that's called Fx. This is the vector field. Okay, so this F is a vector field. F is a vector field. Defined on U. Is a vector field defined on U. Another interpretation is that the mapping F is associating to each point X a vector with the origin in X and the top of the vector, okay, the arrow is at the point X plus Fx. X plus Fx. So that's why this is called a vector field, and this is a two-dimensional vector field, because in 2 dimensions we can build a phase portrait. Okay? Okay. Under specific assumption, we can prove a theorem of existence and uniqueness, saying that locally there is a unique curve tangent to x. So essentially, you remember from when we define nonlinear systems, x dot is fx. Fx was always tangent to the trajectory of x. Fx is always tangent to the trajectory of x. We also have the definition of covectors, because we consider the dual space now. Okay, covectors. Okay, covectors. The dual space V star of some space V, okay, it's the set of all linear applications defined on V, taking values back in R. Okay, these elements are called covectors. These elements are called covectors. As linear applications, the covectors get a matrix representation, yeah, because they are linear. Okay, so linear applications. Linear applications. Linear applications. Okay, and since they are linear, they can get a matrix representation. Okay, so if you have a V, if you have V, a vector in the space V, the dual of this guy is V star, W star, okay, which is a row vector, look at it, in the space V star. Hence, the value of W star in V is given, and this is how you define W star. By this relation, W star V is this is scalar product. This is a scalar product, if you look at it, a scalar product. You also have covector fields. Covector fields. Okay, covector fields. It's a smooth mapping associating to each point X an element from the dual space of Rn. From the dual space of Rn. If W up to W1 up to Wn are smooth mappings defined on a subset U of Rn, taking values in R, we can define the covector field Wx, this guy, this row vector of functions. These are all functions of the point X. These are all functions of the point X. Okay. An important covector field is the gradient, or the differential is the gradient, okay, of some function lambda defined on U, taking values in R. U is a subset, I remind you, U is a subset of Rn. Okay. And you can define the gradient. You can define the gradient, which is the covector or the row vector of derivatives of the function lambda with respect to each component of the vector x. And the notation we usually have is this one. If you remember, we had Lyapunov candidate function. Okay, Vx, you remember, positive definite, V0 is 0. And we were defining V dot x, yeah, because this x is x of t, actually, x depending on time. X, this is a vector from Rn, okay? Vx, so V is defined on Rn and taking scalar values in R. Okay, this is this sort of mapping. And then V dot x, which was actually dvxt to dt. We are applying the Leibniz rule, and it was dv dx times x dot t. And this dv dx was the gradient. This was equal to dv dx1 dv dxn. So this was the gradient. We already know this notion. That's what I'm saying. We have already encountered this notion when we were talking about Lyapunov functions. Okay, so it's a covector field. That's what it says. And if you remember, this was called no, it's like this. Sorry, it's this. Okay, a covector field that has the shape of the differential of the derivative of some function with real values called lambda. It's called an exact derivative or an exact differential. Okay, and now we introduce another geometric concept, Lie bracket. Lie bracket. The Lie bracket. Okay, so the derivative of some function lambda along a vector field. Oh, you remember the Lie? No, sorry, not Lie bracket, the Lie derivative. This is the Lie derivative. You remember, again, we did this when we are talking the derivative. I'm sorry, it's not the bracket. The bracket will follow. Okay, so the derivative of some function along a vector field, it's this scalar product and it's this function. So it's the co-vector of differentials times the vector field, and has this shape because this is dv d lambda dx1 d lambda dxn times f1x f2x and so on fn x. And when you do this multiplication, this is d lambda dx1 f1 x plus d lambda dx2 f2 x. These are all scalars. These are all scalar terms. Plus and so on and so forth. Plus d lambda dxn fn x. Okay, this is also scalar. Okay, and we have this notation L index f of lambda x. If you remember, instead of lambda in Lyapunov candidate function, okay, so v dot x, because we were discussing v dot x earlier, so we just recall v dot x is dv dx fx, so it's essentially lv f lf vx, lf vx. You remember this from Lyapunov theory in the previous chapters. Okay, so we also met this notion before. Okay, now you can repeat. We can repeat this operation with another function g, So lg of lf of lambda is d. So you call this hx. So this is dh dx gx, and h is lf lambda. So you get this relation. Okay, this relation. Now you can do this derivative inductively up to level k. K being any positive integer, and you have lfk lambda x. This is the LF essentially. Okay, this is the LF. This is the LF of LF times k minus 1 lambda. Then it's d lambda k minus 1 dx times fx. And for 0, it's the function itself, no derivative. The Lie derivative is telling us how the function lambda is varying along the solution of the differential equation fx. This is what we used to do when we are talking about Lyapunov energy functions. We do v dot x to understand the evolution of the energy along the trajectory, along the dynamics, x dot is fx. Now we have the Lie bracket, or Lie product. Lie bracket, or Lie product. Okay, Lie bracket or Lie product. Okay, so like I said, we need these differential geometry notions. Okay, so now if you have two vector fields f and g, the Lie bracket between f and g is dg dx times fx minus df dx times gx. Okay, these are partial derivatives where df dx and dg dx are the Jacobians this time. Okay, so if you have a function f Rn to Rn, you remember Jacobian, okay, because we used to do that when we were doing linearization. Df dx is a matrix this time. Df1 dx1, df1 dxn, df2, sorry, dx1, df2, dxn, and so on and so forth. And finally, it's dfn, dx1, up to dfn, dxn. And this is the Jacobian matrix, or is the Jacobian at point x of the vector field f. Okay? So this is matrix. So it's essentially this guy belongs to Rn itself. Belongs to Rn once again. Because this is Jacobian times a vector minus Jacobian times a vector. So matrix vector, matrix vector. When you do the multiplications, you get vectors. You can repeat this just like any product. And if you do it k times, you do this notation, add f to the power k gx, and this is the Lie bracket between f and add f k minus 1 gx for all k larger than 1, and for 0 we have that a add f0 g is gx itself. Properties of the Lie bracket. Properties of the Lie bracket. Okay. Properties of the Lie bracket. So this is a bilinear product over R. Bilinear product over R. F1 and F2 and G1 and G2 are vector fields, and R1 and R2 are real numbers. Then R1 F1 plus R2 F2 Lie bracket with G1 is R1 F1 G1 plus R2 F2 G1. Okay, and also if you shift the operation, it's like this. So this is bilinear product. That's why it's called it's not a linear product, but a bilinear product. It's anti-commutative. It's called. It's Q commutative essentially. It's Q because of this minus sign. So Lie bracket of F and G is minus Lie bracket between G and F. Let's check this out. So Lie bracket between G and F. Definition. It's dg dx fx minus df dx gx. True? You agree? No? No. Sorry. Sorry. df is the other way around. It's df dx g minus dg dx f dg dx fx, and this is indeed minus dg dx f minus df dx g, and this is indeed by definition minus the Lie bracket between f and g. So this is correct. Skew. Skew commutative or anti-commutative. And also the bracket satisfies some sort of additional property called the Jacobi identity. The Jacobi, so if you have three vector fields f, g, and p, then you get this relation. F Lie bracket with the Lie bracket of g and p plus g and so on. This is 0. Now we also have to introduce the so-called distributions. So we need, as you can see, a lot of mathematical tools. They are not very easy, what can I say? But we need all these mathematical tools to be able to understand what's going on. Hidden dynamics, zero dynamics, and so on and so forth. So we assume we have D vector fields F1 up to Fd. Okay? In each point, the vector fields F1, Fdx are generating a subspace of Rn. Subspace of Rn called delta x span of F1 up to Fdx. The object associating to each point x a subspace generated by the values in x of the vector fields, of the smooth vector fields, it's called distribution or a smooth distribution. Okay, this guy, span of F1 up to Fd. This is the distribution. A distribution is defined on an open set U, and it's called non-singular if there is an integer d such that the dimension of delta x is d for each x in U. Okay, it's called non-singular. If there exists, again, if the dimension is constant for each x in U. A point x naught in U is a regular point for the distribution delta if there is a neighborhood U naught of x naught with the property that delta is non-singular on this set U naught. Each point in U which is not a regular point, it's called a singularity point or a singularity. Okay, so we have these interesting definitions. Okay, let's have a break for a few minutes, and then we continue with all these notions and their applications to feedback linearization. I'll see you in a few minutes.
Okay.
Sure.
Okay, I'm back. Thanks. Okay, I hope you're still here. Are you here? Okay. Right. Another important property of these of the distributions is the involutivity. Involutivity. The distribution is called involutive if the Lie bracket, between any two pair of vector fields tau1 and tau2 in the distribution delta, it's also a vector field from delta. Okay, it's also a vector field in delta. So this is essentially the definition. Checking this property is checking it's a rank property, just like controllability. And if you look closely and if you check this for linear systems, okay, then you'll probably get the rank condition of the controllability matrix. Because look at this. So you have to check this rank of the distribution f1 up to fd. Okay, that's the dimension. This is the dimension of the distribution, essentially. This is also the rank of this guy, where you take all the Lie brackets between fi and fj, between the vector fields in the distribution. Okay, so you have this distribution f1 up to fd. Then you do the Lie bracket between any of the functions fi, fj, with the indices I and j between 1 and d, and then you check the rank. If the rank of this guy, which is, like I said, close to the dimension, it's essentially the dimension of the distribution, is the rank of the whole of this guy, okay, then indeed, this distribution is involutive. Okay, you see, this is added extra, but then you have to check this between all the Lie brackets between fi and fj. And now we also have to introduce the so-called change of coordinates. So if you remember from linear systems, okay, so recall from linear systems, okay, so you had x dot is ax plus bu and y is cx. A change of coordinates meant that you had the new coordinate z equal tx, with t a matrix in Rn times n. Okay, so x is in Rn and z is also in Rn. Okay, this matrix is invertible. And this is a change of coordinates. So you have the new coordinates z and the old coordinate x. And note that x, so from z to x, you go back doing this operation, t inverse z. And now you take the derivative with respect to time of this relation. Okay, so you get, this is equivalent to saying x dot is d to dt t inverse z, but t is constant, so t goes out, and z is the one that's getting the derivative. Z is the one that's getting the derivative. So now we substitute this relation into our system. So t inverse z dot equals a tz, this is x, plus bu, and y is c tz. Of course, since t is invertible, we can multiply this relation with t. And then you get that in the new coordinates, the system is z dot is t sorry, T inverse here, and also T inverse here. Okay, so it's T A T inverse Z plus T B U, and Y is C T inverse C T inverse Z. So the new system in the new coordinates, the system in the new coordinates, okay, you have Z dot is A tilde Z plus BU, and Y tilde is C tilde Z, B tilde here, okay? With A tilde is T A T inverse, B tilde is TB, and C tilde is C T inverse. This is the linear case. How about the nonlinear case? Well, in the nonlinear case, this is just a function phi. This is not linear any longer. So you consider the new coordinates in the new coordinates z equal phi x, where phi is this vector field phi 1, phi 2 up to phi n, with the following properties. Phi is invertible. It is invertible in a function sense, in the sense that phi inverse composed with phi is phi composed with phi inverse is the identity. So that means that phi inverse of phi x is equals phi of phi inverse of x equals x. This is what you assume. Okay, in the linear case, t is invertible, implies automatically that you also it's also a function, a mapping invertibility. But the linear case is a particular case of this part. Okay, so of this notion of change of coordinates. Okay, here, so changes or coordinate changes. Okay, and that's what we talk about here, coordinate changes. Okay. Furthermore, both phi and phi inverse are smooth. Okay. Most of the times we are happy with local coordinate changes defined around some point, of course. So essentially we do this locally. If the Jacobian of phi is non-singular, is invertible in some point x naught, then phi is defining a diffeomorphism, or no, sorry, not pH. Diffeomorphism in a neighborhood of x naught. In a neighborhood of x naught. Okay. So in the new coordinates, so you start from this equation. Okay. And also you also have this output equation. The change of coordinates is z equal phi x and x equal phi inverse z, because we said it's functional, it's mapping like invertible. And now z dot. The z dot is dz to dt. Leibniz rule is d phi dx times x dot. Okay, so this x dot means dx dt. Okay, so it's d phi dx times fx plus gxu. X is phi inverse z, so you substitute x as phi inverse z in this guy, and also substitute it in this guy. And then you get these new functions f bar, g bar, h bar in the new coordinate z, just like in the linear case. Okay, where f bar is d phi dx times fx, evaluated evaluated in phi inverse z, so it's in z coordinates. Hx, yeah, this is h of phi inverse of z. Okay, and this one is also evaluated in phi inverse of z. So it's just like the linear case. Linear case is a particular instance for phi x equal tx. Okay, linear. Okay, t constant, t in r n times n. Okay, right. And now let's apply all of this. Let's do an application of all of this for feedback towards feedback linearization. First of all, so we have nonlinear state feedback for single input, single output systems. Okay, so nonlinear state feedback for single input, single output systems. Okay, and we have local changes of coordinates, full linearization or complete linearization, partial linearization, and an application. Okay. Okay, let's see about the linearizing the input-output linearization around some point x naught. So input-output linearization with a feedback, okay, around some point x naught. Okay, so it says here successive differentiations of the output in some neighborhood of x naught. So you just differentiate the output. You take deeper and deeper evolutions. Y dot, y second, and you do this derivative up to an index r. This is going to be called relative degree at some point. That's why it's called r, this index. Okay, you take the first derivative. Y dot is hx dot, and that's dh dx times x dot. Okay, so y is hx. Okay, then y dot is hx, all of this dot, and this is dh dx times x dot. And x dot is fg fx plus gu. X dot, look here, is fx plus gu. Hence, you do this, and then you realize you have dh dx times fx plus dh dx times gx. Okay, so this is dh dx times fx plus gx u. So this is dh dx f plus dh dx gu. So this is L f h, Lie derivative of h along f, and this is the Lie derivative of of h along g, of the same function h along g, LGH. Okay, yeah, exactly. But LGHX is 0. Okay. Why is it 0? LGH. So the derivative of h along g. This is assumed, this 0 actually, he forgot to mention. Okay. So this is assumed. Assume the LGHX is 0. You assume this. Okay, so this is an assumption. This is a crucial assumption. If this is 0, then you're left with LFHX. Okay. Y dot. Now, y dot is the derivative. So this is d to dt y dot. Okay, so you have to do the derivative of this. So this is it's this guy. So this is DLFH times x dot. This is x dot. Okay. So you have LF2H plus LG LFH. But this is 0, then this is 0. If this is 0, then this is 0. Okay, because you can also commute these things. This is 0. So you're left with this guy. You're left with this guy. And so on and so forth. You keep on doing the derivatives, and you stack up these terms. You stack up these terms, except the final term, when you take the r derivative, and this is no longer 0. This is no longer 0, or it's something. So essentially, these are all assumptions. Okay, so these are all assumed. Okay, so I'm just writing here. These are assumed assumptions. So these are all assumed to be 0. And the last term, so if this is not 0, if this guy is not 0, then you can build u, then you get u to be this guy. You get u to be this guy. Okay? And this, if you take this, you'll get the final representation that y differentiated r times is v. This is a chain of integrators. This is a chain of integrators because to get back to y, so you have y derivative r times, you take an integrator, then you get y differentiated r minus r1 times. You take another integrator, this is y differentiated r minus 2, and so on. And finally, you get y dot. You take an integrator, and then you get y. That's why this is called a chain of integrators. This is a chain of integrators. Okay? So you can do this if you have this property satisfied. Then we introduce the notion of relative degree. Okay, a single input, single output system. So relative degree. This is a very important notion for nonlinear systems and for nonlinear control systems in particular. Okay, because based on this relative degree, you can build state feedbacks, just like we said a few minutes ago. Okay. Sorry about that. Right. So this system is said to have relative degree r in some point x naught if LGLFK times h is 0 in some neighborhood of x naught for any k less than r minus 1, and at level r minus 1, LGLF r minus 1 hx naught is not 0. Okay. Some remarks. Relative degree depends on chosen output, so it's kind of conservative. Okay, so it depends on the output you choose. Of course, it depends on h, because not h is satisfy these properties. Okay, there are points where the relative degree cannot be defined. There also exists output functions, output mappings, for which the relative degree cannot be defined in any point. So there is no relative degree. So it depends very much on the output. And you'll see if you check it closely, if you check this property for linear systems, where is it? Okay, so like homework. Okay, check this for linear systems. For linear systems where y is cx. Y is, sorry, x, not capital X, but small, okay? Cx. You see? Look here. So you have x dot is ax plus bu. Y is cx. Y dot is cx dot is, okay, and actually u equals 0. Oh no, leave it like this. Is cax plus cbu. Okay, you assume cbu is 0. Assume cb, cb, yeah, is 0. Then you get cax. Then you have y double dot is cax dot. This is ca times ax plus bu. So this is ca squared x plus cabu. Assume this is 0 again. You get ca squared and so on. Okay, up to n minus 1. Up to n minus 1. Okay, up to n minus 1. Ca squared x. Okay. So essentially, you get that y dot, y double dot, up to y n minus 1. Okay, this is ca squared cn to the power n minus 1 x. You recognize this as the observability matrix Q. Observability matrix. And the relative degree is n in this case. If the relative degree is n, okay, then actually the system is observable because the rank of this guy is also n. Okay, so it's all related to what we know from linear systems. Example, an input based or a van der Pol oscillator with a control a controlled van der Pol oscillator, a controlled van der Pol oscillator. Okay, so these are the equations that define the van der Pol oscillator. Now pick the output y equal to x1. Then y dot is x1 dot is x2. Y double dot is x2 dot is minus x1 plus this guy. Okay, so this term here is not 0 in u. The term in u is not vanishing. Hence, we stop here. Stop. Hence, the relative degree is 2 because you stop at the second derivative. What if you take the output to be x2? If the output is x2, automatically y dot is this guy, and the relative degree is 1 because you stop at the first derivative. See? Stop at the first derivative. What if you take this output? Then you still have a relative degree 1. Relative degree 1. Another example is a linear system. So you see now we go back to the linear systems. So it's expanded in this example. Linear systems are expanded in this example. Okay, which is very nice because it's always nice to understand linear systems. Okay. So again, as you see, LFKH is this guy. LG LFKH is this guy. The relative degree R is characterized by these properties, this and this. Okay, so the relative degree is the difference, it's actually the pole zero excess. Okay, the difference of degree between the numerator and the denominator of of this guy, of this transfer function, okay, of the transfer function. Yeah. This is what the relative degree is. So essentially, the relative degree is how many poles you have over how many zeros you've got. Over how many zeros you've got. This is what relative degree does for linear systems. Okay. A check. So now we explicitly look at this. This is a rational. Okay. If you remember, this transfer function for linear systems is a complex rational function. This is a complex rational function. Okay. And if it's complex, then this is something like Rs over Ps, a quotient of two polynomials. And we assume we have these two polynomials, assuming, first of all, the denominator is monic, because we have the leading term equal to the leading coefficient equal to 1. And m is less than n, so the denominator, yeah, the denominator is of degree m less than the denominator. Now we write here a standard controllable realization, okay, a canonical control realization of this transfer function, okay, of this transfer. Just do recall this from last year's lecture or in dimension and complexity reduction, where we discussed quite a lot. We had a recap, a famous recap of linear dynamical systems theory from the second year. Okay, just keep this in mind. Now, this is a controller canonical. Sorry. Oh shoot. Controller canonical form. Canonical realization. Controller canonical realization. Okay, that's how it's called this. Is this form. Note that this matrix A is a companion matrix, of the polynomial Ps equal Sn plus an minus 1 Sn minus 1 plus a0 is a companion matrix of this guy. It's a companion matrix because any polynomial has an infinity of companion matrices, as we all know. B has this form and C has this form. Okay, this is very easy to see because what? Yeah, from this transfer function look of things. Okay. Well, so we have CA is 0. Okay. What? C times A. Oh, and take C to be of this form. Yes, indeed. And now when you do C times A, you look at this. So this is from 1 to m, 0m. So this is m plus 1, and this is m. Well, wait. So from B0 to Bm, you have how many coefficients? M plus 1, yes? So this starts from m plus 2 here, up to n. Okay, up to n. Okay, cool. So when you do CA, you get C times A. You get like this. All right. C is this guy times A. So it's B00 up to M. And then, why do you still have these terms? B0 up to Bm. Because, oh yeah, sorry. This is the first. So the first one is 0, indeed. The second one is B0. Yes, sure. Look, multiply this C with A. Okay, so B0 times 0 on the first, so this line with the first column. B0 times 0, that's 0. B1 times plus B1 times 0, that's also 0. Up to M, and then it's all 0. Fine. So the first element is indeed 0. Now multiply this C with a second column. B0 times 1 is B0, and then it's all 0, and so on and so forth. And indeed, here you get from B0 up to Bm. B0 up to Bm. So CAB is indeed 0. Look, multiply this guy with B, and you get 0. Multiply this guy with B, and you get 0 between n minus. So when you stop here, okay. Now, if you do not stop here and you go, now you go and occupy the last position with this M. Okay. Note that all these covectors essentially, they belong to R1 line times n. Okay, and this is also n times 1. Oh yeah, it says here. Okay, so finally the final one is this. So M is indeed no, n minus m, sorry. That means that the relative degree is n minus m, indeed. Okay, very interesting. Right, the line vectors dhx0, dlfhx, and so on, these are all linearly independent. So we have some implications of the relative degree. So we have this line. These are all independent. These vectors are all independent. So necessarily, always the relative degree is less than or equal to n. And we make these definitions, and we can use these things. Okay, this function might have a non-singular Jacobian. So essentially, we want to create with these LFs a coordinate transformation. Note that all these functions can be chosen such that LGFI equal to 0. Okay. Furthermore, the values in x0 can be arbitrarily chosen. Hence, with this phi made of these ingredients, we build up a coordinate transformation. Okay. And for all the new coordinates from Z1 to ZR-1, where R is so a representation in the new coordinates. Okay. All right. So once we do this, we show what happens for each coordinate. So Z1, okay, so you pick the coordinate transformation Z equal fx, where fx is given by this guy with these functions, okay? If you do the computation, Z1 dot up to ZR-1 dot are linear are linear equations of this form. So it's like a controller canonical form, if you look. That's what we'll get. And finally, the last one has this form, ZR. All the other Z's from R plus 1 up to N, okay? Okay, assuming that this is 0, assumption, okay? Assuming that this is 0, all the rest of them from R plus 1 up to N have this form, Hence, we get the so-called normal. We get the so-called normal form of a nonlinear system. Normal form or no form of a nonlinear system, and this is the normal form. This is the normal form, where ZR, you see, has the control U, and all the rest of them are these functions QR defined like this. These are going to actually induce the notion of zeros of a nonlinear systems. We have an example. Okay? But let's have a break first, and in 10 minutes, we look at the example and carry on, okay? Are you still here? Hello? I'll see you in 10 minutes, okay?
Yes, no problem.
Okay, I'm back. So let's look at an example. We have the DC motor. DC motor. Okay, example. Okay, we have the DC motor. V is the voltage. V denotes voltage. I denotes current. L is inductance. R is the resistance. Omega is the angular velocity. J is inertia coefficient. Bm is friction coefficient. B is friction coefficient, and this is load torque. This is load torque. Okay, and some assumptions. VR is a constant input. Okay, the friction coefficient is 0. The tau L is a constant load torque. Okay, input is U equal to Vs. State variables, states. The states are x1 is the current Is, x2 is the current through the resistor IR, and the angular speed x3. The output, so what do we need to measure when we talk about a DC motor? We need to measure the angular velocity. Okay, this is what we usually control. Okay, so this is the controlled measured output. Okay, controlled measured output. Notations, we denote by θ1 the coefficient Rs over Ls, θ2 and so on. These are just coefficients. So the theta's, these are constant coefficients. Constant coefficients. These are constant coefficients. Okay. And if you substitute all these notations, this system becomes this state space dynamical nonlinear systems. Look, this is nonlinearities. This is a nonlinearity. This is a nonlinearity. So we have this polynomial-like couplings. So for zero perturbation, equilibrium points. The equilibrium points are 0, θ5 over θ3, and omega, with omega real, and relative degree of this guy, you can compute at home, is 2 around this equilibrium point. So we compute just like you saw earlier. We compute this coordinate transformation. So we denote this by CT. So we compute the coordinate transformation. Where is it? Compute the coordinate transformation CT. Okay, this is the CT because we have 3 states. This is the coordinate transformation CT. Okay, and we apply this coordinate transformation with no particular choices of the functions from relative degree R to relative degree from R plus 1 to N. Okay, so relative degree is 2. So essentially, you need to compute here another phi 3. So this is phi 1, phi 2. This is clear. and this is phi 3. Phi 3. Okay. Yeah. So once you compute this guy and you apply this coordinate transformation on this guy, you get the normal form of this DC motor. You get the normal form of this DC motor. Okay, that's what you have to do. So essentially, you apply this. You can apply this thing, or you can just compute phi. You can just compute phi. Okay, and apply it to this guy, and you get the normal form. Okay, so you can do the computations yourselves. Now, the general normal form. So without choosing, with no particular, so the general normal form. General normal form. Okay. No particular choices of the functions phi r plus 1 to phi n. You can get this. So up to the relative degree r, you get this linear part. For the relative degree r, you get this equation, which is controlled. And then all the other equations, all the rest of the equations, they're also controlled by this u guy. And the output is chosen y equal to z1. This is the general normal form. And now we have an example for this. We have an example of this. Yeah. So the example of this is this polynomial system. Note that this is truly nonlinear system, truly weak nonlinear system. This is the output we choose. This has relative degree 2 for all points where x3 is not -1. Okay, so relative degree 2 for all points 2 for all points where x3 is not -1, and the global coordinate change that takes us to the general normal form is this coordinate change. Z1 is hx, Z2 is LF hx. Note that this has relative degree 2. And then you can pick, they said that the rest, so phi 3, so this is phi 1, phi 2, phi 3 and phi 4, any choices. So there is no particular choice. So we took the simplest. We chose the simplest form for phi 3 and phi 4. Okay, this is the simplest form of these guys. And it takes you to the to the general normal form. Okay, right. So you can try to do these examples yourselves in Maple if possible. Try these things in Maple if you can. Okay, it's interesting to see how these things do work. Okay, I think you should use Maple. You need not do it by hand. Okay, you can always use Maple for this. Okay, maybe we can try this after the lecture. We can try to open a Maple sheet, and we can try something about this. Okay, right. Now, full linearization, full state feedback linearization. Full state feedback linearization. So the normal form for R equal to n. So relative degree equal to n. We can have that. You know, usually the relative degree satisfies this relation. Now this time we pick the relative degree to be the dimension of the system. So for R equal to n, you extend the normal form and you get all these linear equations, so essentially here you have 0, 1, 0, 0, 0, 0, 1, 0, okay? And this this stops with a 1 here, okay? This matrix. And you can multiply this with Z1 up to Zn, okay? So this can be written in this form. It can be written in this form. And then Zn dot, so this is an extra equation, is this one. The final equation is this one. Okay. This is not an invertible matrix because this is a wide matrix. Okay. So this is R n minus 1 times n. Okay. And this is the final equation where you apply the control. Okay, so this is identical. If you look at this, is not identical. Is similar to the controller canonical form. To the controller canonical form. Okay. And if you pick this input, you get a linear controllable system, which is this one. This is the linear controllable system. This is full because the whole system is linearized. Yeah, this is the closed loop system. This is the closed loop. The closed loop system. Okay, it's very nice. So the whole closed loop system. So essentially, you get this. This is the nonlinear system with the state x. Okay, and you do this. You do this. So U is this guy. No, this is in the state Z. Sorry, this is nonlinear system in the state Z. And you do this, and you have the controller U. Okay, and this guy. Sorry, not this guy. But this guy. This guy is in controller canonical form. This is in controller canonical form. This is very nice. Okay. Now the question to be answered is, when can this be done? So when can we do full feedback linearization? Under what assumptions? Okay. And now we have conditions to perform full state feedback linearization around a point called x0. Full feedback linearization around x0. Okay. The existence of an output function, existence of the output hx, for which the system has relative degree n, is not only sufficient. Okay, so output, existence of the output such that r equal to n is necessary and sufficient, for feedback linearization, for full state feedback linearization. Okay, this is necessary and sufficient. Such a function, so h of h exists if and only if rank rank of all of this matrix is n, and this distribution is involutive, around x naught. A necessary condition for full state feedback linearization is that the linear, this is necessary, the linear approximation around x naught is controllable. Okay, linearized approximation around x naught is controllable. This is a necessary condition. Necessary condition. This is a necessary condition. Okay. So if you have this this rank condition, this is and you can do this necessary condition, then indeed you can do full state feedback linearization. Algorithm. An algorithm for full state feedback linearization. Algorithm for full state feedback linearization. Okay. If you have the vector fields f and g, you build the vector fields g, addf. You check the formula for addf. We have the formula earlier with Lie brackets. This is with Lie brackets. And you check conditions I and 2I. So you check these conditions. Okay, you have to check these conditions. Okay. If I and 2I are satisfied, then you solve the partial derivative equation, the PDE. Okay, PDE. You solve this PDE. Then you compute the control law with alpha x. I remind you, U is alpha x plus beta x v. And you pick alpha and beta to be these guys. Finally, you build the coordinate transformation or the coordinate change. You build this coordinate transformation. And that's it. You apply this coordinate transformation and you do full feedback linearization. Homework. Apply this algorithm to the linear system. X dot is ax plus bu, and y is cx. Apply this to this system and see what it looks like. Okay. And here we have an application. So we try to do an app, full state feedback linearization around the origin of this nonlinear system. Okay. We compute lambda x1, and then, okay, so we take this hx, and we do this change of coordinates. Okay. Of course, we need to have phi x not equal to 0. If this condition, if you want to do stabilization, so now you want to stabilize at x equal to x naught. You want to do this stabilization. And indeed, you can achieve this. Okay. Now, we can also do partial linearization. Okay. We do have unobservable, so partial linearization. partial linearization. And first of all, we have to look at the unobservable dynamics. So it's about observability. It's like state estimation this time. Okay. Right. Now, when R is less than n, partitioning the state vector in like this, psi equal to z1 up to zr and eta zr plus 1 up to zn, the normal form is written in this form. Gets this form, the normal form we had earlier. Now, the control law of this form brings the dynamics of eta to become unobservable for the output of the specific relative degree R. Okay. Furthermore, we assume that x naught is an equilibrium point, and that psi equal to 0 and eta equal psi equal to 0 and eta equal to 0 in x naught. Hence, in the new coordinates, the origin is an equilibrium point. The origin is an equilibrium point. And now we talk about the zero dynamics. The zero dynamics, okay, is actually mimicking the so-called transmission zeros in the linear case. Transmission zeros in the linear case. Okay. So output zeroing. The problem of output zeroing. Okay. So you need to find all x0 and u such that yt equal to 0. That's unobservability. This condition implies that z1 is 0, z2 is 0, up to zr equal to 0. So psi t equal to 0, because this is the partitioning, the partition of the state we have already done. Okay. And the input u has to satisfy necessarily this condition, because zr is also equal to 0, if you remember. Okay. Hence, ut has this particular form, and eta is the solution of the differential equation, of this differential equation. This is the zero dynamics. This is the zero dynamics. Okay, so where this dynamics goes to 0, you cannot see it in the output. That's zeros. Hence, you need psi 0 to be 0, whereas the condition on eta 0 is arbitrary. So essentially, you need to satisfy this guy. Okay. Now, a particular case, zero dynamics of linear systems. Zero dynamics of linear systems. Okay. Now you have this transfer function, irreducible transfer function. Okay. And the relative degree. Okay, a relative degree is R. Look at the coefficient. Look at the degrees of the polynomials. Okay, relative degree R. You assume this. The zero dynamics is given by this system. The characteristic polynomial is corresponding to the numerator polynomial. Look, because this is a companion matrix. This is companion matrix. This is a companion matrix of the numerator of HS. I'm writing this like in MATLAB. Okay. Analogously, the nonlinear system with stable zero dynamics are called minimum phase, because when the zeros of a transfer function are stable, and the system is stable, of course, we call this transfer function a minimum phase system. And here we have an example. This is a nonlinear example. Okay. The zero dynamics of this system, zero dynamics. So it only has a zero, okay? So probably relative degree is 2. Okay. So this is stable. This is stable. So this is minimum phase system, and probably the system itself is also stable. Okay. Now, if we go back to the DC motor, in the new coordinates, the normal form has this form. And for Z1 equal to Z2 equal to 0, the zero dynamics is this guy, which is also stable because θ3 is a negative constant. This is also stable. So it's minimum phase. Okay. And now we have the zero dynamics for general normal forms. We can compute this, and the zero dynamics has this form. Okay, so zero dynamics for general normal forms. Okay. And here we have another example. Okay. And of course, there is the problem of reproducing a reference output. Okay. Okay. So here we have a generalization of the notion of zero dynamics. And we have the problem, okay, of tracking a reference output. Okay, so you impose an output and you want to track this. So you want to find all the pairs. Find all the pairs x naught and u such that y is yr. Such that I is yr. So you impose these conditions, and then the conditions imply that the ith derivative, I minus 1 derivative or of IR is ZI. And you do this state, this coordinate, you take this coordinate psi r, and it's necessary that the input u satisfies this relation. So this is the input you have to take on the system to do this, and this is the zero dynamics. The zero dynamics, okay? The zero dynamics has a special form such that that particular output, reference output, is followed. You can also do dynamical inversion. You can also do dynamical inversion. Okay. So you find the control. You find the control to ensure tracking of YR. And this is the control law. This is the control law. And this is the zero dynamics. Okay. And you can also do local asymptotic stability. Local asymptotic stability. You take this particular control law. Okay. And in closed loop, the closed loop system. Okay, so local asymptotic stabilization. Okay. This is the closed loop system, and this is the A matrix. Note that this is a canonical form A matrix. Okay, is the companion of this polynomial. If the equilibrium point eta equal to 0 of the zero dynamics is locally asymptotically stable and all the eigenvalues of the matrix A have negative real part, then the control U is locally asymptotically stabilizing the origin. the origin. Okay, and here we have some remarks. We can also do asymptotic. So it has all this feedback linearization, all this zero dynamics idea has, which is a consequence of the feedback linearization, has a lot of applications. For instance, we can do asymptotic tracking. So this is nonlinear control again. And we can find a control that tracks a specific reference. This is the error. This is the error, and the error can be zero, and be made zero. And here, all of this is applied. All of this is applied to a DC motor, and it shows you a PD, a proportional derivative controller. Okay. Okay, so DC motor control application. Okay, and this is a PD controller, proportional derivative, nonlinear. Okay, controller. It shows you how this is done, and it shows you how to implement it, how it's implemented. Okay, and it follows if you see a step function. It follows a step function. Okay, so this is pretty much the idea of feedback linearization. The next time we are going to look at other slides and other explanations of feedback linearization. Okay, have you got any questions, please?
Currently not, but I think like in the beginning of January there will be a lot of questions from my side because I start to.
No worries. I look forward to you asking them to me.
Yeah.
Please do them and do the assignments as well, and tell your friends and your colleagues to do the same. Okay. All right.
Yes.
Okay. So have Merry Christmas first of all. Okay. I hope you accept this wish because nowadays you don't know. Okay. So Merry Christmas if you celebrate Christmas.
Yes,
Happy
no worries.
Sorry.
No worries about it. It's
fine. Okay, fine. No, you know, I'm not pretty much a politically correct guy, so I usually speak my mind. Okay. Have nice holidays and fruitful holidays, and we'll all meet again after. So here now next week the winter holidays starting, and the lectures are resumed after the 10th of January. So we are going to meet the first time on the 13th of January, okay? We don't have much lecturing to do any longer, so please try to select the papers for the exam and try to start studying now. Now you have to start studying. You also ask your colleagues to select an examination date, please, okay, an exam date. And we'll talk more about the exam and everything after the holidays. Okay, so please tell your colleagues as well, or also ask them to look at this lecture and listen to all these indications I'm giving. Okay, so once again, happy holidays, and hope to see you back safe and sound. Okay.
Yeah. Thank you very much. Also,
No
Merry Christmas to you.
Thank you very much.
Yeah, stay safe until next year.
Yes, I'll try to. Okay. See you in January. Bye.
Yeah. Thank you very much. Merry Christmas. Bye.
Bye.